So residential wiring, so if we're using three-phase power everywhere to transmit power around, right? But then in my house, I get, or even one of these wall outlets, I get single phase. How do I do that? Well, very simply, you pull the power off of one of the three phases, right? So when we looked, I mentioned that in our systems here, like if we use three-phase here in the building, the most common three-phase to have at a point of use is 208 three-phase, meaning that it's 208 voltages across the line. So that means that what we take is we measure across this point to get the VL, right? And this is 208 volts because of that √3 factor that comes into play when each of these single phases is 240 volts. Sorry, not 240, 120. Yeah. Yeah, 240, right? No, 120. Sorry, my bad. 120. Yeah, 120. Okay. So we call that the 208 three-phase, but that's when we have all three phases connected, right? So then there's some load over here as well. However, if I take this branch here, if I just pull in two of the phases, right? But I'm not concerned about the phase difference between them, right? Then across from the neutral point to one leg, I have one phase, and that gives me 120 volts. From the neutral point to the other phase gives me 120 volts. And if I take the voltage across the two, there's a 240 volt difference. Right? But I'm not connecting that third phase. So it's only the one relative to the other, which makes it relatively simple to deal with, right? So when you look at a distribution panel, which you guys did a lab last semester with the distribution panels, right? If you're looking at a circuit breaker panel, there's sort of a bar down the middle, right? And they run the two phases off each of the sides, and you can connect to one to get a single 120 volt, or you can connect a double breaker. Sorry, it's actually a jump across like this. There are more on the other side of the distribution panel. But every other slot connects to one of the two different lines coming in. So if I connect it across both of those, I'll get a 240 volt system. And so that's what's shown in this residential wiring diagram. Right? So coming in from the street, the voltages are very high. That's another way the power company saves on the cost of the wires. Because if I want to deliver the same amount of power, right, I want to minimize the amount of current that I have to flow so that I can shrink the diameter of my wiring, and I can do that by raising the voltage. And so that's why power companies transmit their power at very high voltages. Many kilovolts, 13 kilovolts. Actually, some systems run on 400,000 volts and more, right? They have extremely high voltages. And they go through a series of substations. When you drive along the side of the road and you see like that thing that looks like a mini power plant or something, right? Those are substations where the large transformers are making adjustments from one voltage to another to send down to the residential areas or to bring in power from a couple of different generator facilities, right? And so those big substations are full of transformers changing the voltages. We're going to learn a lot more about transformers starting in this week, right, with chapter 13. But in the case of basically, right now, just think about a transformer as something that allows you to change the voltage. And in its simplest case, when you preserve the power. So if I lower the voltage, I raise the current. So when I get to a house, I can go through a step-down transformer. I have really high voltages over here. I go through this transformer that reduces that voltage dramatically, but increases the amount of current. But now I only need larger wiring right here in the house for a very short distance. Not for the many, many miles this may have traveled. Right? And so when I step down into the house, again, I get 3 wires that will come to the house. One is the neutral point, which is attached to the ground outside. And then the other 2 are 2 of my lines that come down and into my, well, they go through your meter and then into your power panel, which is full of circuit breakers, which are like a switch or a fuse, right? Or switch and fuse, essentially. Old ones were fuses that actually burn out when too much current flows through them. Now, there's a couple of different methods that either based on the temperature of the thing or the magnetic field that's generated, it'll actually pull a physical switch over. And those are much nicer, circuit breakers, because you can just go downstairs and flip the switch back over and turn your power back on once you've corrected the problem, right? And so you'll see then in this, relatively simple case, here's your main lines that come in from the power meter. So there's a mains disconnect that shuts off your entire distribution system in your house. And then you feed into your distribution panel, which does something like this, right? Where you have smaller individual circuits that feed 120 volts by connecting to the neutral and one of the lines to the neutral and the other line. And they don't show on here a 240 volt system or a 240 volt circuit, but a 240 volt circuit would be connected across both of these outer lines, typically with a 3rd wire as well. So when you're looking at wiring in your house or anywhere else, you'll see a variety of different numbers of wires, right? And those can be related to the type of power that you have available, right? So you can have 2 wires, right? 2 wires are like simple lamp cords. I don't know if, I don't think we don't even probably have anything in here. Well, somebody's pulled the ground pin off of this one, right? But it still works with just 2 plugs, right? The hot wire and the neutral, and that neutral returns the power, right? But then we have our 3-pronged systems, which are like this one, right? That has the ground wire. But then you can also have 240 volt single phase systems where you can have 3 wires on those, which are the hot, and the neutral. Or you can have a 4-wire single phase system that's 240 volts, which is the hot, the neutral, and the ground for additional safety, right? So you might have a 4-wire system. Or you can have a 3-phase system. A 3-phase system needs at least 3 wires, right? You can have a Y-connected system that gives you a neutral, which gives you a 4th wire. Right? Or you may have a Y-connected system with a neutral and a ground, which gives you a 5th wire. Right? And so you can't always know exactly from the number of wires that you see what type of a system it is, but you can have a pretty good idea, right? If you see 4 wires, you know it's not a standard 120 volt system, right? Because a standard 120 volt system only needs 3 wires. And if you see 5, you know it has to be a 3-phase system, right? So it can kind of help. And then, how do they kind of, have all these different systems working together? It comes down to code. We don't often talk about, it's kind of strange because as engineers, you'll live and die by the code, right? But we don't often talk about the code in school because it's really just a collection of industry best practices and regulations. And so the National Electrical Code is produced by the NFPSA, I think it is, National Fire Protection Safety Association, something like that. Basically, it's produced by the people who want to make sure buildings don't burn down, right? And so they produce the National Electrical Code, which has developed over many, many years, and every year or 2 they'll put out a new version, And that new version includes, the best, most up-to-date practices based on equipment and things that are available, always with an eye toward safety. Right? Some of those regulations are for efficiency and whatnot, but typically they're focused on safety. So they have rules about, how many of these circuits you could have connected to a main panel based on the amount of current that's available or things like that. They try to avoid having the switches, the circuit breakers have to open or close too many times, right? They have rules about, well, how many light bulbs could I connect to circuit number 1, right? They'll have, so if I have a basic wiring in a room, they may say, okay, if these were all incandescent bulbs, you can only have 10 of them hooked up to a single circuit. Why is that? Well, because they say, well, normal circuits are wired with 12 gauge wire. It can carry so much current, maybe 15 amps of current. So you put it on a 15 amp breaker, and an incandescent bulb, if you put 10 100-watt bulbs in, you'd burn 1,000 watts of power, right? Which would be on a 120 volt system, somewhere near 10 amps. That starts to get near the limit of the wire, so they say that's enough, right? Build in a little bit of a safety factor. Now, of course, things like fluorescent lights and things, they take way less power, so that's, there are some different rules involved. So the National Electrical Code really then becomes what you implement when you actually decide to put the wires inside of the building. And if you were to go to work as a, like a construction trades type of an electrical engineer, so if you're like a contracting engineer or a consulting engineer, which many of our engineers end up going out into the building industry. Many of the mechanical engineers go out and are hired into firms to work on HVAC systems, right? How do you make sure you get proper flow of air and heat and cooling and things into the buildings, right? Many electrical engineers end up consulting on the wiring systems of a building, right? And so you will have to reference that National Electrical Code all the time, right?
Because last week I was sizing 2 pumps for motors.
Okay.
It was based off of the feeder circuit breaker, the main circuit breaker, and then the conductor of the wire for each of those.
Yeah, so you have to decide what gauge of wire you're going to use and all of that kind of stuff. And all those things have to be specified by the engineers on the project. And you write it into your drawing. Did you have to do blueprints for an electrician to follow?
Yeah, it was based off, I had the NEC book right in front of me.
Yeah, there you go, see? So it happens, it really does. There's proof, right? You actually do have to follow the rules, right? So, again, a lot of it is kind of common sense, right? But a lot of it is just, again, it's like, well, what size wire do you use if I need to carry 20 amps of current, right? What size wire is safe for that? And the code will tell you, like, what size of wire you need to use. Or will tell you, you better go find one that's rated for that amount of current, right? So, right? And so, those are good practices. So I highly, I recommend that you be familiar with, you don't need to go read the code. Nobody wants to read the code. It's impossible to read.
It's too big.
It's like that thick. It's horrible, right? But you should be aware that it's out there. And so, know that that is something you might need to reference in the future. You can get little shorthand books for most standard stuff as well. They have little summarized versions. Yeah, and the little like the little contractor guidebooks and things like that as well. So yeah, there's a few of them out there. But anyway, so in residential wiring, we typically don't see 3-phase systems, but in our industrial systems and things we do. So like, in fact, if you go over to the lab, I have a couple of 3-phase outlets that I got wired in last year last summer when we were moving over here to this building, right? Because we have some 3-phase systems, 3-phase motors that we want to be able to run in that lab. So they put me in 2 3-phase outlets, right? And so when you walk into the lab on the back wall, just the other side of this wall right here, you just look along the wall and you'll see the panels with a really strange looking plug, right? That has like 5, I think they're 5 wire that they put in, right? So there's actually like 4 blades around the edges with a center pin in the middle as well. And you're like, what the heck would plug into that? Well, it's a 3-phase system, right? And so that's one of the other ways that they do it. There are several, NEMA is another body that sets a lot of helpful standards. And so NEMA actually certifies particular styles of plugs, connectors, and receptacles for different types of usages. So there will be, you know, a certain NEMA style for a 3-phase, you know, 30 amp circuit. There will be a different style for a 40 amp circuit, right? And that's because, again, they don't want you to accidentally plug a cable that's only rated for 20 amps or 30 amps into a circuit that might provide 40 amps. So they make sure that, again, by the code, you're required to ensure that whatever receptacle you install is only, if it's rated, a receptacle is rated for 40 amps, the person installing it has to make sure that the wiring to that receptacle is rated for 40 amps, and that there is no more than a 40 amp circuit breaker in the distribution panel. It wouldn't be safe to put a 60 amp breaker in the distribution panel with wire that can only carry 40 amps, right? And say, well, I'm just never going to plug anything in that takes more than 40 amps. Well, that's really dangerous, because as soon as the next person comes into that building, they may say, hey, look at that plug. I can plug in this giant thing into it, right? I'm going to plug my stove in, right? My stove takes 60 amps, and whoops, you know, then they cause a fire because they pull too much power, and the breaker won't cut off and protect it, right? So a lot of this, again, becomes what you hear about in terms of regulations and things is really oriented around safety. The thing may perform, and that's something you do have to be careful about with engineering, right? We may be able to get something to work, but just because it works in a lab or with somebody who's really careful and is really paying attention to what's going on, doesn't mean it's going to be safe for general population use, general consumption, right? Like, I do this, right? Sometimes, turn off my